Recording is rolling. It is Wednesday, April 24th. Right, so we're gonna finish this statistics adventure today. You're in stats pack at puzzle C. So Friday we did part A. Yesterday we did part B. Today we're gonna do part C. Right, and then the last 2 minutes of class we're gonna start on this quantum mechanics journal, right, which is remember why we're even doing stats in the first place is I think if you guys have an understanding of statistics and probability that quantum mechanics makes a lot more sense, right? But in the class, I'm going to give you guys this quarter page and also some paper. I'll have you guys staple. Oh, are there some staplers possibly being passed around from last class? Yeah, I see one over there, right? So I'll help you guys put together what's going to become a quantum mechanics journal. We'll take the next few days to do these quantum mechanics topics. All right. So right. First of all, a little bit of recap here, what you guys seen so far. Because again, a lot of guys have only seen this like 2 days ever in your lives and just been what we've done in class. Okay. So we've been thinking about data probabilistically, which we haven't done in this class up until last Friday, right? So like in this class, it's like, okay, things have definitive properties. Like definitely has like so many kilograms fast, and it's moving in so fast meters per second. This is this location, right? But not really anymore. Right, so we're going to start thinking probabilistically. I'm going to say, like, what is the height of a tree? Well, that does not have a definitive answer. What you can do is you can maybe survey thousands of trees, right, and say, okay, maybe put their heights in this bar chart, right, and then step back and look at it. Maybe some kind of bell curve emerges. And I'm really simplifying a lot. Right? Not all data in the world is going to line up in a bell curve, right, that's normally distributed, right? But a lot of it does. This is kind of foundational, fundamental statistics, and then you can get more complicated from here, right? But maybe this is a different way of seeing things, right? You can determine things probabilistically. Say, okay, well, there's some mean value, right, which is like the peak of this bell curve, right? There's also the standard deviation. Think of this sort of like a plus or minus value, right? Like how wide is this distribution, right? Right. Do you guys here? Let's see if you guys remember this from last few days. Right? If I have some mean value of something, I say plus or minus one standard deviation. Right? So from this inflection point to this inflection point, that's going to cover what percentage of all this population? What percentage? 68. That's 68%, right? Which is about 2/3, which leaves about 1/6 of the data to land on this extreme tail, and the other 1/6 to land on this extreme tail. In this case, maybe it's like really short trees and really tall trees, and then about 68% is okay. Is it? All right. So we did that. All right. Yesterday I had you guys also measure each other's heights. So you took your height and your friend's heights and say, hey, can we turn that into like a normal distribution bell curve? And the last question you answered was, well, depending on where you rank within your friends, and assuming that models something about the larger population, right? What percentage of people could be taller than you, right? So say like if you had a z-score of maybe somewhere here, somewhere between -3 and +3 possibly, right? Because that covers almost the entire bell curve. Say you have a z-score of 2. That means you're really tall among your friends, and there's out in the wider world maybe only a few people that be taller than you there, right? We could consult the z-table. So this tells you, like, if you know z-score, right? Remember the left half of the table is below average with negative z-scores. The right half of the table is above average with positive z-scores, right? If you know your z-score, right, how much of the curve is filled up to that point, right? And that's what the table values tell, right? So you're above average for you're above like what percentage of people would be like shorter than you in this case, right? Okay. So if you want to figure out like what is this white tail, and that's the last question you guys answered yesterday with you and your friends and the meter sticks, right? You have to take the table value and subtract it from 1, right? So if you were so tall that you were, let's say you had a z-score of exactly 2, so you were 2 standard deviations above the mean. That means I'm going to round this to like 97%. Okay, so I'd say, okay, great, I'm taller than 97% of people. That means I'd be shorter than this last 3% of people. Okay, all right, so there you go. All right, so that's a review of what you guys have seen last few days. All right, so you guys ready for part C? All right, so everybody put their packet of part C. All right, here. All right, so I've got 4 questions, 1, 2, 3, 4, with 2 scenarios. You've got the scenario on the left and the scenario on the right. And there's one new idea from today, which is we're going to start putting objects into groups, right? Like put people into groups, put water bottles in groups, right? That's going to change the standard deviation, which is going to change how we think about this, right? And so we got a formula here. Here's mean average, which you guys have probably known since elementary school. Here's standard deviation. We did one of those out on paper on Friday, and then from there on, I showed you how to put it on a calculator. There's z-score, which is a count of how many standard deviations from the mean, right, which could be positive or negative, above average, below average, right? Here's going to be the new one, is what is the standard deviation for a group, right? Now, the first question doesn't quite do that, but that's going to pop up here in a few minutes, right? So what is this first scenario? Suppose the average human height is, right? You guys have an average human height, right? Now, of course, everybody's numbers are a little different, right? But my paper says 177 centimeters, right? You guys have an average height that's, well, probably something different than that, right? And a standard deviation of so many centimeters. My paper says 9.0 centimeters, right? So if I do 177 centimeters plus or minus 9 centimeters, according to my numbers, that should cover 68% of the population. And then you get some people who are super tall and some people who are super short beyond that, okay? First question, what is the expected value of the height of the next person who walks in through the door? Let's say it's completely random. It could be, you know, any one of 7 billion people on Earth could walk through the door, and, you know, right? Just right. Suppose you had money on the line. You're going to make a bet, right? Guys, what's probably the best number to put in this box right here? Yeah, just take the average value, right? I mean, that's probably as good as anything else, right? Or if you can make it incremental, if you go centimeter by centimeter, right? So if you kind of rounds to the nearest centimeter, right? That would be like the tallest bar in a bar chart, because it'd be like the plurality, right? Yeah, so probably your best guess is just go ahead and go with the average, right? You say, right? And what would be the standard deviation for our next individual person? Oh, well, just, you guys think you're gonna copy paste that number right there? There you go. Right, so just the given value. So given value, given value. Okay, so everybody's definitely got the first two boxes, right? You just copy pasted the numbers that I gave you. Okay. All right. Oh, therefore, what is the percentage chance that the next person has a height greater than or equal to? Even taller number than that. My paper says 185 centimeters. Obtain a z-score and then consult the z-table. Or z-table, right? So let's get a z-score for, right, notice, and I think the story is probably somewhere on your paper. I'm picking someone who's already above average height, right? What's the percent chance that someone's even taller than that, right? Well, guys, is this percentage definitely going to be less than 50%? Right? Okay, it's got to be less than 50%, right? But let's figure out exactly what is the answer to that. Okay, so I'm going to find z-score. You guys remember how to get z-score, right? It's the count of number of standard deviations. I'll take the individual values, subtract the mean. That right away will tell me are they above or below average, and then divide by standard deviation. I'll call S, right, to get a count of the number of standard deviations for the mean. So if I plug some numbers in, my target value is 185 centimeter. Right? I'm going to subtract the mean, which is 177 centimeter. Of course, I'm doing my numbers. You guys are doing your numbers. Right? Okay. So right away, I see this is a tall person, right? Above average tall. But how much above average tall? Like if you compare them to all people in population, are they just a little bit above average? Are they crazy above average? Well, that depends on the standard deviation. So I've got a standard deviation of this many centimeters. So now I'm about to get a count of how many standard deviations above the mean is this individual. You guys got that? A little bit of review from yesterday. We did this too. Right? So that minus that in parentheses, all divided by that. Right, I'm looking at, okay, so I'm getting a z-score of 0.89. 0.89, right? So that's kind of in that average range. It's on the part of the bell curve that's still concave down, right? So it's kind of in that average-ish range, right? Above average, but not crazy above average, right? Right, so I've got a z of 0.89, right? Did you guys figure out what your z-score is? Right? Right, now let's go take a look at the z-table, and that'll tell us where this individual ranks in the population. So 0.8, right? Now remember, as you go to the right, you get one more decimal of precision. So this is, you guys see the numbers across the top, 0.00, 0.01, 0.02. Okay, so look at the hundreds place. So here's 0.80, 0.81, 0.82. Now if I want 0.89, I need to go all the way to the right column, right? Here's the cell I'm looking for right here. Bam. Let me zoom in where you guys can read what I'm looking at, right? You guys see that number says 0.8133, right? Can I interpret that as about 81%? Right? You guys think 81%? Right? Now, remember what that means. That means that this person is taller than 81% of people, right? The amount of bell curve you shaded and under that curve, right? Up to that point is 81%, right? But the target question is, not that part of the bell curve, but this white tail right here is how many people are even taller than that. Well, guys, if the shaded region is 81%, then what is this white tail? What percent? 19, right? Because doesn't 81 plus 19 add up to 100% of everybody, right? And that's the answer to this question. So let's show you guys right here. Okay. I took 100%. I subtracted 81%, which I got from the Z table. I got a Z score of 0.89 that corresponded to 81%, rounding a little bit, right? And that tells me 19% is in the right, in that extreme tail, right? So I got a Z score of like, all right, so we haven't quite hit that inflection point. This part's 81%. Means this tail right here is 19%. Okay, right, guys got that? Okay. That's the answer to this question. 19% would be even taller than that, right? Okay, that looks about reasonable. Okay. Right, guys.
What is going up and down on the Z chart do?
So
how you do it?
Okay, so how do you read the Z table, right? Okay, so see the left column says Z, and right. Now, if you have a positive Z score, you're focused on the right half of the table, right? It starts at Z of 0. Now, Z of 0 means 0 standard deviations from the mean, which means you are at the mean. And then the first cell tells you exactly 50%. So yeah, if you were right at the mean, then you'd be taller than exactly 50% of the population.
Okay.
Right. And then as you go down, you get more and more extreme Z's. So here could be a Z of 1 right here, which means 1 standard deviation above mean, which probably corresponds about what the picture is showing, because it looks like that Z value is right at the inflection point, pretty close to, right?
So if up and down is Z, then what's left?
Left and right is precision.
Oh.
So say I get a Z, like suppose you want a Z score.
I get it.
Okay, yeah. All right, so for anybody else who needs to see it, if you had a Z score of 0.80, that's this cell. If you had a Z score of 0.81, that's this cell. 0.82, 0.83, and so I had a Z score of 0.89, so I went all the way over to 0.89. That's how I got that number. Okay. All right, yeah. Okay, so everybody on same page now? All right, so we're all good. Okay. Again, that's I think kind of similar to what we were doing yesterday so far, right? So we got a good review so far, right? Because now we're about to bring in a new idea, which is to put people in groups. Right? So this question here, use the same average height and standard deviation as before, right? What is the expected average height for, let's say, a group of 5 people who walk in through the door? So now we're not looking at a single individual. We're going to let 5 people walk through the door, and we're going to take their average height and say, what's the expected value, right? Here, I'll have you guys guess, and I bet a lot of you guys might guess the correct answer. What number do you think is going to go in that box right there? Yeah, same number as before, right? Same average as before. It's still going to tend towards the average. In fact, I think it's going to tend more strongly towards the average, right? The more people you let walk through the door and take the average of that larger and larger group, it's definitely going to tend towards this mean, right? In fact, if you let all 7 billion people walk through that door, and you take the average of all 7 billion people, well, now kind of by definition, you're mashing the entire population of right, the entire world, right? So it's definitely going to be that number, right? Does that make sense? Right. But what about standard deviation for a group of people? Well, if we got a larger and larger group, and we're taking the average, that we can more definitively predict that the average of a larger and larger group is going to tend towards the average of the population in general, right? And think about what that would do to the bell curve. It's going to change the bell curve, right? Here, let me run through an example with you guys in case you don't quite see this, right? Like this bell curve was showing heights, let's say like heights of people that walk through the door, right? So there was some little short guy that walked in, but he was like the only one, right? A lot of people that walked in were kind of average, and oh, we got one like super tall guy. He was like 7 feet tall. Wow, right? So he shows up like once, right? But if you put people in groups of 5, what's the chance that a group of 5 people are all collectively on average short? Well, now that chance is like almost 0, right? So this tail is disappearing. But what's the chance that group of 5 people walk in and on average they're 7 feet tall? Well, one guy might be 7 feet tall, but an average of 5 people at random? Now that chance is almost 0. So now that tail is also disappearing, right? So do you guys think that this bell curve is like getting squashed like this? It's getting skinnier bell curve, right? You guys see, right? Okay, so if we're putting people in groups, it's definitely tending towards the mean. Now we're a lot more likely to land something closer to average for a group than we are for an individual. Individuals are like more sporadic, right? Is that right? So I bet the standard deviation is going to get smaller, 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 right? Right? You guys see that? See the bell curve getting squashed like that? Is that for a group, right? And the math is this expression right here. I'm going to write this bigger on paper. Okay? So it says standard deviation for a group. Remember, I'm using sigma and s interchangeably just for this class, right? Is what it is for, say, like an individual, divided by the square root of the group size. N could be the number of people in the group. Okay, is that? So I'll do for a group of 5 is now for my individual, I'm saying 9 centimeters. Remember, think of that kind of like a plus or minus factor, right? Plus or minus 9 centimeters covers most of the people, right? Now I'm going to divide by the square root of 5, which is going to make the standard deviation smaller. Which would match like a narrowing bell curve, right? With a smaller standard deviation, which is 9 divided by the root 5. Okay. I'm looking at 4.02, I'll call it 4.0. Oh, and it would still be centimeters. So it has the same unit as before. Okay, right. So now we have like a smaller plus or minus factor, right? You guys get that? Okay. So that's the answer to this box. We round that to 4.0 centimeters. Okay. Okay. You guys good so far? Okay. Is there any question about this? Everybody's got their paper filled up to this point now? Of course, with your own numbers. Okay. All right, so therefore, what is the percentage chance that the average height of the next 5 people walking in is, greater than 185 centimeters, right? Well, for an individual who was to be super tall, like this is super tall, before it was only 19%, which not that great, because we're not super tall people, right? But for an entire group of 5 people to walk in and their average height also be super tall, guys, is this percentage going to be bigger or smaller than before? Smaller. It has to be smaller, because for everybody to be walking in, they're all super tall. That would be probably a pretty small chance. Now, how small are you talking about? Well, let's run the numbers. So z-score I need. So let's do a z-score for this group of 5. So same as before, I would take my individual target value, which in this case is 185 centimeter. Okay, subtract the mean, expected value 177 centimeter. Okay, so that's same as before, same as before. This entire numerator is the same as it was before, right? But this standard deviation is going to be different from before, right? Before it was 9 centimeters, now it's only 4 centimeters, or whatever numbers are on your paper. We got like a shrinking standard deviation. Okay. You guys see a smaller denominator is going to correspond to being a larger z-score, which is going to put us out further on the tail of a bell curve. Okay, so what's that minus that in parentheses divided by that? I'm looking at a z-score of 2.0. Yeah, that's getting up there more. Like if you're 2 standard deviations above the mean, you're pretty far out on the tail at that point. Okay, so I'm going to put 2.0. It's got a z-score of 2.0. Okay, you guys figure out what your z-score is? I got 2 exactly. Maybe we could throw in one more decimal place, do something like that. Okay, you guys good? Okay, so let's see z table. Where are we on this bell curve? Okay, there's a z-score of 2.0. Now mine is like 2.0 on the dot, 2.00. So this first cell right here says 97.72%. Okay, so that 97 point. So 97.7%. That means, so we're talking about groups of 5 people. The chance that they're like that height or shorter is like 97.7%. Well, guys, if this is 97.7%, then what is this white tail here? Is that 100% minus that? Right. So it's 100% minus 97.7%. That is 2.3%. And I think that also makes sense. Right. It looks about right. Right. Passes the smell test, you could say, right? 2.3%. Okay. Right. So let's pause here and zoom back, big picture, like forest for the trees here, right? For an individual to walk through the door who's super tall, I mean, probably not going to happen. But okay, 19%, right? Almost a 1 in 5 chance that they're going to be super tall walking through the door. Okay, it's going to happen sometimes. There's some tall people in the world, some tall individuals. But if you're putting them in like groups of 5, and you say like on average that group of 5 for them to be collectively super tall, that's almost never going to happen. And for them to be that tall or taller, that's only going to happen maybe about 2% of the time, right? Does that make sense? Right, that was a big, right? Okay, all right, you guys good so far? Now, what's so this is all there's a connection to quantum mechanics, right? So let me give you guys some scenarios of at least what one of the connections is going to be, right? There's a few connections where it's nice to know probabilities of bell curves, right? But okay, is uh maybe I'll start with an say like an analogous story. Let's do it. Yeah, analogous story here, right? So we'll keep people and we'll keep heights. What if you're an alien in a flying saucer and you're flying around Earth, right? You look at surface Earth, and your job is to report back to alien base on some other planet. Tell us about human civilization. So you're making this observation. You're keeping all this observational data. You're trying to figure out something about how do people live their lives, right? And one thing you notice is that okay, I see people. It looks like they wake up at like 6 o'clock in the morning. They all go to these jobs. It looks like I see them running around. Right? You can't really see inside the building, so you have to make some kind of inferences, right? And one thing you notice is that it looks like there's like these stadium type buildings have these domes on them, so I can't see what's going on inside. But I do see like these groups of 5 really tall people regularly walking into the stadium. I wonder what's going on here. So you start piecing together this evidence and you start make pretty good like grounded hypothesis for what the heck people are doing right inside these dome buildings where you can't see inside. See, and the hypothesis that you stumble upon eventually, the data supports is, I think there's this game that I'm going to tag with the name basketball. I think there's this game called basketball that people are playing. And I think what happens is that there are these teams of 5 people, and they must be doing something that being really tall would give them some kind of special advantage. And that's why they're hanging out in these teams of 5, right? Maybe there's like some like high level they have to reach or something, right? You have this, you piece together the story that probably is actually pretty close to what would represent basketball, right? You say, well, if basketball did not exist, then to see like teams of really tall, five really tall people walk around together, that's almost never going to happen. This might happen once in the history of this entire planet. I see like 5-7 foot people walk around together, right? Right? But I see that all the time. That would be a statistical anomaly if it were truly random. So I don't think it truly is random. I think that there's this game that I'm calling basketball, where there's an incentive to have groups of 5 really tall people walking around together. That would make sense, right? Right. So you're hypothesizing that this game basketball exists, right? You guys kind of see that, right? It's based on probabilities, Right? Okay. So quantum mechanics. Part of quantum mechanics is particle physics, right? Do you guys see over there on the wall? There's a poster that says standard model on it. Standard model. Let me find a poster for this. I gave you guys thumbnail notes a few weeks back for relativity, and on the back side were printed posters for quantum mechanics. Right? So you guys do have these posters already. Okay. Let me point this out. Okay. So a few weeks ago, you guys remember those thumbnail notes for relativity? If you flip the page over, you guys already have these, right? Hey, look, a bunch of posters for quantum mechanics related. See quantum mechanics. It's a bunch of topics we're talking about for the next week. Okay. And one of them looks like this standard model. Right. So okay, so there's some particles that exist out in the world, right? I see photons. Okay, they could be like particles of light. I see electrons. Okay, so maybe familiar with those. Right? What about some of these other ones? Right? Like, have you ever opened up a textbook and seen a picture of a photon or a picture of an electron? Right? Okay, that's not really a thing, right? What about this Higgs boson, which was kind of confirmed to exist back in 2012, right? Is there like a picture of that? Can you like Google Higgs boson? Oh, there's a picture of Higgs boson. That's how it, no, right? So how do particle physicists know that these exist, right? Well, the standard model started out as math on paper back in, I think, the 1970s. It was. They worked out mathematically. A bunch of theoretical physicists said, I think mathematically these particles fundamentally should exist. There should be a Higgs boson. There should be an electron. There should be like a top quark, right? Right. And then how do they go about verifying the existence of these particles experimentally? Right. Now we're going to bring in experimental physics. And a lot of these were discovered at a place called Large Hadron Collider. There's an organization called CERN over in Switzerland. There's this huge synchrotron, this particle accelerator. It's so big it actually runs underneath the border with France, and they smash these particles together all day, every day. Right, so millions of particle collisions, and they're gathering statistical data about these collisions. So they have mass data, spin data, charge data, right? And they collect all this data, and based on how these collisions operate, they can say statistically whether these particles exist or not. So back in 2012, the last part of this model to be experimentally confirmed was the Higgs boson. But it's not because anybody has a picture of it, right? It's because based on how these collisions roll out, if the Higgs boson did not exist and they were still getting the statistical data that you're getting, there would be like a something like a 1 in 10 million chance that they would be still getting that data. So for the Higgs boson or any of these other particles to not exist, that would be like winning the lottery, right? Which statistically isn't going to happen. Therefore, we can pretty safely say that all these particles do exist, right? Right. That's one connection with statistics and quantum mechanics, right? Right. So we're putting these collisions in groups, right? Kind of like putting people in groups, right? In this analogy, replace the game of basketball with the Higgs boson, and now you have particles, right? There's some other connections too with quantum, but you guys will see those coming up, right? So we've got one more story example. Right? Before I jump into that, are there any questions so far? Right, pretty good. Right. So the other category story we're looking at is like filling bottles with water, right? So we're back at the factory. We got this conveyor belt of bottles, right? There's some machines filling them up one by one. Next one, next one, next one, okay? And maybe there's a slightly different amount of liquid in each bottle, right? Maybe they're aiming for like 1 liter per bottle, 1 liter bottles, right? But like plus or minus a couple milliliters, right? They're not going to be exactly the same, right? So we're back to that story. Suppose the average volume of water is, now my paper says 1,000 milliliters. Your paper says whatever yours says, right? And I'm giving a standard deviation for a single bottle of like 4 milliliters, right? So if I took 1,000 milliliters plus or minus 4 milliliters, that should cover 68% of bottles, right? You guys got that? Okay. So first question, what is the expected value of bottle water in a bottle chosen at random, right? So pull a random bottle off the shelf, right? Guess what number is going to go in that box? 1,000 milliliters, right? Or whatever your average is. Bam, right? That's your best guess, right? Okay. What's the z-score for a bottle of? Ooh, I got 1,005 milliliters. It says 1,005. Okay, so this bottle's been overfilled by 5 milliliters. Like, how likely is that to happen? Well, I need a z-score. Right. Right. So you guys ready to get a z-score for your paper also? I'll take the target value, 1,005 milliliters. Subtract the mean, which for me is 1,000 milliliters. Right. So okay. So right away I see this bottle is overfilled, right? But how much overfilled compared to all the other bottles? Well, divide by the standard deviation. That'll give me a count of how many standard deviations above the mean this particular bottle is. So is that 5 on 4? I think. Whoops. 5 on 4. It's 1.25. There you go. 1.25. Right. So I got a z-score of 1.25. That's 1.25 standard deviations above the mean. Right. You guys got your z-score? Okay. Right. Next question. Therefore, what is the chance that the next bottle chosen at random has that volume or more? Ooh, that volume or more. So z-table time. Right. And remember, the question being asked is not exactly what's on the table, which tells you how much is shaded up to that point, but we need the target question. How much is this white tail right here? Right. So I got a z-score of 1.25. So here's 1.20, 1.21, 1.22, 3, 4, 5. Here's 1.25 right here. Bam. Let me zoom in on that. Let's that. Right. So this cell is telling me 89. I'll just call it 89%. Can I call it 89%? Okay. Great. 89%. So 89% of bottles have less than that much liquid, which means how many bottles have more than that? Well, 100% minus 89% is 11%. Right? Can you guys see that for your paper too? Take whatever value is straight off the table, subtract it from 100%, and that tells you the answer to the question, how many bottles have more liquid? Right? Guys got it? Right, so back to the page, 11% for me. Right? You guys got whatever you got? We're good? All right. Now the last question, you guys know where we're going with this, is we're going to start putting bottles into groups, because a single bottle is so sporadic and so individual. I mean, I'm in, right? But if we're putting bottles in groups, now we're going to start tending towards the mean, right? So the same average value and standard deviation as before, right? What's the expected average volume for a group of 5 bottles, right? See if you guys are following. What number goes in this box? Oh, same average as before. Same as before, right? Okay. So copy paste that. Right. Ooh, what's the standard deviation for a group of 5 bottles? Right. I remember how we did it for a group. Right, is we took it for an individual, the standard deviation for an individual, and divided by the square root of the number in the group. So I have a standard deviation for an individual bottle of 4 milliliters. I'm going to divide by the square root of 5 because I'm putting them into groups of 5. So what's 4 divided by the root of 5? Right. Did you guys take your standard deviation divided by the square root of 5? Right. I'm getting 1.79, and the unit is milliliters. Okay. Okay. You guys getting whatever for your paper? All right, so put that right here. All right. Okay. All right. Now pause right here. Let's put context to this. Right. What this means is that if I'm looking at groups of 5 bottles, so I got this group of 5, this group of 5, this group of 5, right? Say what's the average volume? Okay. I should expect the average volume to be pretty much in the vicinity of 1,000 milliliters. Okay. Plus or minus 1.79 milliliters should cover 68% of these groups of bottles, right? Not individual bottles, but groups of bottles, right? Notice what happened to the standard deviation went down. That's great. Right? Therefore, what is the collective z-score for an average volume of 1,005 milliliters? Z-score. Let's get z-score. So I'll take the target value, 1,005 milliliters in this case, subtract the mean. Okay, so that's the same as it would have been for an individual anyway, whatever. Okay? Right. But now I'm going to divide by the now smaller standard deviation. Right? Okay. So I'm getting like a narrower bell curve because I'm putting these bottles into groups. Ooh, this is a pretty hefty looking z-score, 2.79, right? And that's a unitless value. It's a z-score, right? 2.79 standard deviations above the mean, right? That's getting pretty far out on the tail, right? I mean, right? Let's see how far out on the tail, because the last question says, what's the chance that we got a group of bottles that's on average filled even more than that? Okay, I bet this percent here. I'm going to make a guess. I'm going to make a guess that this percentage is like less than 1%. Okay, I don't know for sure. We're going to check the z table, but okay. So z-score 2.79. Check this out. So 2.7, and then go all the way to the right for 9. 2.79. That's bam. This cell right here. Zoom in where you guys can see that. Right. This says 99.74%. 99.74%. Right. Now remember what that means. That means that there's a 99.74% chance that these groups of bottles, if you pick a random group of 5 bottles, it'll be less filled than 1,005 milliliters, right? Which definitely makes sense because that's pretty overfilled and putting these bottles into groups. So that would be crazy for a bottle to have more than that, right? How crazy? Well, I need to subtract this number from 100%. So let's do 100% minus 99.74%. That'll tell me this white tail right here. Everybody knows where, to answer the question, you're actually looking for this white tail, right? Okay. So I'm doing 100% minus 99.74%. Is there any question where I'm getting these numbers? Right, you guys are able to follow in your paper too? Everybody's doing it? Okay. 0.26%. Right. Guys, that's not 26%. That's 0.26%. That's less than 1%. Okay. Okay. And of course, everybody's got different numbers on my paper, but I'm going to guess that yours is probably kind of similar to that. It's probably like 1% or less, or kind of close to that. Mine is 0.26%, right? Less than 1%. Yeah, right? It'd be crazy unlikely, right? So if I was regularly seeing groups of 5 bottles that were overfilled, so like more than this volume, that would be a crazy anomaly. In fact, I might think that there would be some reason for that, right? Kind of like the groups of 5 tall people walking together might indicate that there's a game called basketball, right? Or for particle physics, if they're seeing like, hey, why is the spin number showing up so much? Why is it so anomalous? Oh, okay, well, probably because there's a particle out there called like a nut pork or something. Okay. All right. You guys good there? All right. So this whole packet, if you're finished with the entire packet and you feel good about all your numbers, you can turn it in at some point. I'm gonna score each one of these puzzles, A, B, and C. If you either missed a day and you need to go back and watch the video, or if maybe you want to go back and check your numbers for any of these, if you want to take a few days to turn this in, then that's okay too, right? But I need to get you guys these quarter pages for the next thing that we're doing here.